We're going to begin to visualize our variables with graphs. While we start with graphing one variable at a time, we'll use this as a springboard for ultimately visualizing multiple variables simultaneously within our graphs. We're going to keep it simple. We'll use Stata code to generate graphs that help us learn more about our data and to make decisions about next steps in our research. We're focusing on the function of graphic visualizations rather than producing polished presentation-ready graphs. Bar charts are most commonly used to examine the distribution of individual variables. Here we show the distribution for the random sample of 1,200 U.S. college students who were asked, "What is your perception of your own body?" In this bar chart, the X, or horizontal axis, includes the three response categories: underweight, overweight, and about right. In the first bar chart, the height of the bars is measured on the Y, or vertical axis, as the number or count of college students giving each response. The second bar chart shows the same data, but as a percentage of the total sample. A bar chart helps us display the distribution of a categorical variable, for example, percentage of observations in each category. If you'll recall, the data managed variables of interest in our sample project are now tab 12 MDX, representing a diagnosis of nicotine dependence in the past 12 months, and numsigmo_EST, representing the average number of cigarettes smoked per month. If we run a tab 1 command with these two variables, of course the output will include frequency distributions for these two variables. However, in addition to frequency distributions, we now want to examine corresponding bar charts for these two variables. The bar chart is one of the most frequently used graphic visualizations. In Stata, we will use the graph bar command to produce them. Here's the basic code for a univariate graph of a categorical variable. Graph bar, comma, over, parens, categorical variable, close parens. This code shows relative frequency, or percent. Graph bar, parens, count, close parens, comma, over, parens, categorical variable, close parens. This code shows absolute frequency, or number of observations. The command graph bar tells Stata to generate a bar graph for your categorical variable, in this case, tab 12 MDX. The graph shows percentages on the y-axis, that is, the percentage of observations in each level of the named categorical variable. Here's the bar chart code inserted in our sample program, and we just execute the command to generate the requested bar charts. Here's the bar chart we told Stata to generate. It shows the percent of young adult smokers with nicotine dependence. About 52.5% is indicated by the response code of 1, and those without nicotine dependence, about 47.5% indicated by a 0. Now we'll graphically display the frequency distribution for the smoking variable, that is, the estimated number of cigarettes smoked per month, numsigmo_EST. Because numsigmo_EST, which is the estimate for the number of cigarettes smoked per month, is actually a quantitative variable, the syntax we use in the Stata program is slightly different. The command histogram, or hist for short, tells Stata to generate a histogram. To visualize a quantitative variable, you would use the code histogram quantitative variable, which is numsigmo_EST, comma, frequency. The frequency optional argument here is telling Stata to produce the numeric frequency, or number of observations in each bin on the y-axis. Hist numsigmo_EST, comma, frequency. When you run this, you'll see that Stata generates a graphical distribution of a quantitative variable, a histogram. In a histogram, intervals of values are plotted on the x-axis rather than discrete or separate values. From the bars here, you can see what is displayed is the midpoint of the intervals. Typically, we don't specify the width of the bars for a quantitative variable, as Stata will create a display that best represents the distribution. Let's look at a more basic example of how a histogram might be constructed, and then use that as a springboard for talking about additional descriptive statistics that can be generated for quantitative variables. In this example, we have the exam grades of 15 students. We first need to break the range of values into intervals, also called bins, groups, or classes. In this case, since our data set consists of exam scores, it'll make sense to choose intervals that typically correspond to the range of letter grades. So 10 points wide, 40 to 50, 50 to 60, etc. By counting how many of the 15 observations fall in each of the intervals, we get this table. To construct the histogram from this table, the intervals are plotted on the x-axis and show the number of observations in each interval, or the percentage of observations in each interval, on the y-axis, which is represented by the height of the bar located above the interval.
Once the distribution has been displayed graphically as a histogram, we can describe the overall pattern of the distribution and mention any striking deviations from that pattern. More specifically, we should consider the following features. We will get a sense of the overall pattern of the data from the histogram's center, spread, and shape, while outliers will highlight deviations from that pattern.
When describing the shape of a distribution, we should consider symmetry or skewness of the distribution and peakness or modality, that is, the number of peaks or modes that the distribution has. Here, all three distributions would be referred to as symmetric, but they're different in their modality or peakedness. The first distribution is unimodal. It has one mode, roughly at 10, around which the observations are concentrated. The second distribution is bimodal. It has two modes, roughly at 10 and 20, around which the observations are concentrated. The third distribution is kind of flat or uniform. The distribution has no modes or no value around which the observations are concentrated. Instead, the observations are roughly, uniformly distributed among the different values. A distribution is called skewed right if the right tail, the larger values, is much longer than the left tail, or smaller values. Note that in a skewed right distribution, as you can see here on the right, the bulk of the observations are small to medium, with a few observations that are much larger than the rest. An example of a real-life variable that has a skewed right distribution is salary. Most people earn in the low to medium range of salaries, with a few exceptions, such as CEOs, professional athletes, etc., that are distributed along a large range, that is, the long tail of higher values. A distribution is called skewed left if the left tail, or smaller values, is much longer than the right tail, or larger values. Note that in a skewed left distribution, the bulk of the observations are medium to large, with a few observations that are much smaller than the rest. An example of a real-life variable that has a skewed left distribution is age of death from natural causes. Most deaths from natural causes happen at older ages, with fewer cases happening at younger ages. Skewed distributions can also be bimodal. Here's an example. A medium-sized neighborhood 24-hour convenience store collected data from 537 customers on the amount of money they spent in a single visit to the store. The histogram displays the data. You can see that the amount of money spent is concentrated around $20 and then concentrated again around $50. From the Mars crater data set, we also display the latitude of the Mars crater's rims. The values are concentrated around 66 to 69 decimal degrees north, and again around 36 decimal degrees north. So the mode or modes of a variable are the values that occur most often, and knowing this can help you make better decisions. The mode, for example, has applications in book publishing. Not surprisingly, It's important for the publisher to print more of the most popular books because printing different books in equal numbers would cause a shortage of some books and an oversupply of others. Likewise, the mode has applications in manufacturing. For example, it's also important to manufacture more of the most popular shoes and shoe sizes.
Now, as we've seen, the mode is not always at the center. The center of distribution is its midpoint, the value that divides the distributions so that approximately half the observations take smaller values and approximately half take larger values.
As you can see from the histogram, the center of the grades distribution is roughly 70. We can get only a rough estimate for the center of the distribution. 7 students scored below 70 and 8 students scored above 70. Estimates can often be made from examining a histogram. So what about spread? The spread of the distribution, also called variability, can be described by the approximate range covered by the data. From looking at the histogram, we can approximate the smallest observation, or minimum, and the largest observation, or maximum, and thus approximate the range. In our exam score example, you can see that the approximate minimum is 45, that is, the middle of the lowest interval of scores. The approximate maximum is 95, the middle of the highest interval of scores. So our approximate range is about 50 points, 95 minus 45. The overall pattern of the distribution of a quantitative variable is described by its shape, center, and spread. By inspecting the histogram, we can describe the shape of the distribution, but as we saw, we can only get a rough estimate of the center and spread.
In order to describe the distribution of a quantitative variable, you also need precise numerical descriptions of the center and spread.
The mode is a kind of average. There are 3 kinds of average, and each one tells us something different, so we need to make sure we understand what each average means.
When we use the term average, we mean one of 3 things usually. Either we mean the mean average, or we mean the modal average, or we mean the median average. It's very easy to understand the difference between these, especially if you've played darts before. I threw 2 lots of 3 darts, and in my 6 darts I scored a 2, 3 threes, a 12, and a 13. Now let's see if we can work out the mean, the median, and the mode. First of all, the mean. We take the total of all the 6 scores and divide by the number of observations, and that's the mean. If we want the modal score, we simply look for the most common score, the most common number of observations. If we want the median score, we write the scores down in ascending order and then look for the middle value. Now there's a slight problem here that we have an even number of observations, so we take the 2 middle values and work out the mean average of those 2. So for my not very good dart playing, our scores were 2, 3, 3, 3, 12, 13. The mean is 2 plus 3 plus 3 plus 3 plus 12 plus 13 divided by 6. 36 over 6 equals 6. The mode is 3. The median, since we have an even number of observations, is 3 plus 3, the middle 2 observations, divided by 2, which equals 3. Notice if the dart player had scored, say, 19 instead of 13, the mean increases to 7, but the mode and the median score is unchanged.
So let's briefly review numerical measures of center. Intuitively speaking, the numerical measure of center is telling us what is a typical value of a variable's distribution. The three main numerical measures of the center of the distribution are the mode, the median, and the mean. So far, when we looked at the shape of the distribution, we identified the mode as the value where the distribution has a peak. And we saw examples when distributions have one mode, that is, a unimodal distribution, or two modes, a bimodal distribution. In other words, so far, we identified the mode visually from the histogram. Looking at our histograms again, we can easily see the mode. It's the most common occurring value in the distribution. The median, that is, the midpoint of the distribution, is the number such that half of the observations fall above and half fall below. We find the median by ordering the data from the smallest to the largest. Consider when n, the number of observations, is even or odd. If n is odd, the median is the center observation in the ordered list. When the number of observations is even, the median is the mean or average of the value of the two center observations. The mean, of course, can be calculated by adding up the values for all the observations and dividing by the number of observations in order to generate a mean average. Our goal here is to describe the distribution. How would you describe these two distributions of exam scores? Both distributions are centered at 70. The mean of both distributions is approximately 70. But the distributions are really quite different. The first distribution has much larger variability in scores compared to the second one. In order to describe a distribution, we need to supplement the graphical display not only with a measure of center, but also with a measure of the variability or spread of the distribution.
There are several ways to describe spread. A commonly used measure is standard deviation. The idea behind the standard deviation is to quantify the spread of the distribution by measuring how far the observations are from their mean. The standard deviation gives the average or typical distance between a data point and the mean. In order to better understand standard deviation, it would be useful to see an example of how it's calculated. In practice, of course, the software will be doing these calculations for us.
Emergency medical services companies would like to estimate how many ambulance crews to keep on standby. Here are the number of ambulance calls over an 8-hour period. To find the standard deviation of the number of hourly calls, first we would find the mean of our data. Next, we would need to find the deviations from the mean, that is, the difference between each observation and the mean. Since our mean is 9, we would subtract 9 from each of our observations. As a third step, we would square each of these deviations. Next, we average the square deviations by adding them up and then dividing them by n minus 1, that is, 1 less than the sample size. This average of the squared deviations is called the variance. The standard deviation of your variable is the square root of this variance. So why do we take the square root? Note that 16 is the average of the squared deviations and therefore has different units of measurements. In this case, 16 is measured in squared number of ambulance calls, which obviously cannot be interpreted. We therefore take the square root in order to compensate for the fact that we've squared all of our deviations, and also in order to go back to the original unit of measurement. Recall that the average number of emergency calls in an hour is 9. The interpretation of standard deviation equal to 4 is that, on average, the actual number of emergency calls each hour is 4 away from 9. Another way of saying this is that there's an average of 9 ambulance calls in each hour, plus or minus 4. Since we're working with very large numbers of observations, hand calculations of standard deviation really aren't feasible. Stata will do all these calculations for you, but it's important to know how to calculate standard deviation so that you can make sense of variability. For example, looking at a variable's distribution in two different samples, you should be able to tell which has greater variability, that is, a larger standard deviation. To calculate the standard deviation using Stata, we use the summarize command, abbreviated sum, and then a list of quantitative variables that we'd like to examine. We're going to execute sum with numsigmo_est as the quantitative variable. When we execute the summarize command, Stata provides us with the univariate statistics for the number of cigarettes smoked per month variable. You might notice that this table generated by the summarize command for our variable numsigmo_est shows 1,697 observations rather than 1,706 observations in our sample. This is because the summarize command shows summary statistics only for all valid observations, leaving out any that are missing the value for the particular variable being summarized, since missing variables cannot be quantified into mean or standard deviation, etc. In order to determine the number of missing observations, we can use the command count if numsigmo_est == dot. When we execute this command, we can see that 9 observations are missing. When we go back to the table generated by the summarize command, you can see the mean, the standard deviation, the minimum, and the maximum. So you can see that sum is extremely useful in better understanding important characteristics of the cigarette smoke per month variable. We now know that the young adult smokers in our sample smoke an average 320 cigarettes a month. Given that the standard deviation is about 274, we can say that, on average, young adult smokers smoke 320 per month plus or minus 274 cigarettes. So as you can see, there's an extremely large range in terms of cigarettes smoked and a lot of variability on this variable. But why didn't we add the nicotine dependence variable to the sum command? It's very important to remember that most of the univariate statistics are not appropriate to calculate for categorical variables, particularly nominal categorical variables. If you'll recall, the nicotine dependence variable is represented with dummy codes. That is, a yes is indicated with a 1, and a no is indicated with a 0. If we were to include the categorical variable for nicotine dependence, tab 12 MDX, in the summarize command, Stata would still generate summary statistics based on dummy codes. The means in this case will represent the proportion of 1s in our sample. So again, it's very important to remember to use the appropriate descriptive statistics for both quantitative and categorical variables. To briefly review, descriptive statistics for categorical variables, which entails the number of observations and relative frequencies of each group within that variable, can be generated using the tab 1 command. Descriptive statistics for quantitative variables, which entails the mean, range, and standard deviation, can be generated using the sum command.